Today we will take up this principle of Contra gradients. There is only one principle. Using that, you can derive the relationship between the global stiffness matrix and the local stiffness matrix through a transformation matrix R. That is the thing now. The principle of Contra gradients, if the element displacement vector, if the element displacement vector, that as per our notation, it is called dm. That is, according to local coordinates, the element displacement vector at the ends of the member. The element displacement vector dm is related to global displacement vector. It is related to global displacement vector, which we denote by the symbol ds, system displacement vector, as dm is equal to r into ds. Here, r is called transformation matrix. And of course, the elements of Rij, any element Rij, that is the element belonging to ith row and jth column, is obtained by applying a unit load along the coordinate j, that is global coordinate, corresponding global coordinate, and determining the corresponding displacements, components of displacement in the element coordinates. So that exercise, if you do it, already have done in TRES problem, applying a unit displacement along the global coordinates one at a time and determining the corresponding displacement along the global coordinate member directions. So like that you can evaluate all the elements of R. So if you do that exercise and obtain R, and you call the relationship between global displacement and element displacement vectors by this R, like this. Suppose if you have that relationship, then according to this principle of Contra gradients, then according to principle of Contra gradients, the forces, the global forces is related to element forces by transpose of this transformation matrix. This is what that principle states. It is a very simple principle. Suppose if you have a transformation matrix R which relates the global and local displacements, then you can relate the forces in local and global in reverse pattern in this fashion through transpose of same transformation matrix. So that principle we call a principle of Contra gradients. So it is a very simple, straightforward principle, which of course you can use for development of this stiffness matrix relationship. So this, when you have, we have Ps is equal to Ks into ds, and Pm likewise the force displacement relationship in local and global coordinates are like this. that you have seen already. The source in global coordinates at the nodes and the corresponding displacements in the same global coordinates, they are related through what is known as stiffness matrix in this fashion. Likewise in local coordinates also. Forces in local coordinate is connected to forces through global coordinate through stiffness element stiffness matrix. This is element stiffness matrix where Km and Ks are element and global stiffness matrix. Global stiffness matrices. Km is element stiffness matrix and Ks is global stiffness matrix. So you substitute these two in the second relationship. So substituting Pm and Ps into we get Ps is Ks into Bs, that is Ps from this. Okay, then that is equal to RT into Pm is nothing but Km Dm. RT Km Dm. But Dm is RDS from 1. But from 1 Dm is RDS. Therefore, Ks Ds is equal to RT Km or ds. This ds, if you take it out, you will get this Ks is equal to RT Km R. This is the relationship between the global and local stiffness matrices. That's what I have told. It's a very simple exercise by knowing the relationship between global and corresponding local force displacement relationship, and by applying this principle of Contra gradients, so you can just connect the system and global stiffness matrices. Already we have used this in our problem, stress problem. So we know the element stiffness matrix, that is A by L, JE by L, 1 minus 1 minus 1, 1. That I have derived. Knowing that stiffness matrix and knowing the transformation matrix, so you can straight away derive the global stiffness matrix, which is helpful for solving the problem. So all these transformation matrix and other things you need not bother to derive. So you can straight away use it, and of course that we apply in our finite element method of analysis. Straight away we can use the global stiffness matrix and then use this relationship, because this is external load is known, this is known, we can evaluate the displacement. Then once displacement is evaluated in global coordinates, corresponding displacement in local you can determine. Then knowing the member stiffness matrix, you can evaluate the embedded forces. In just 3 steps, you can finish off the evaluation of the problem. So, next, how to derive this principle? I told you now it is a principle. So this principle also can be easily derived by applying the strain energy principle, that is external material to internal material. That particular principle, if you use it, straight away you can derive the principle of Contra gradients. So that also you can just take it. So we can say derive equation to derive this equation, to this principle of Contra gradients, I will derive, right? So, you have this relationship, this is known, then the external work done is equal to, by the system of forces in local and global directions. So we can say that is equal to ds into dst. That's the external work done. Force into displacement. Global direction force. The forces acting in global direction is known. Corresponding displacement also you can measure it. So you can find out the external work done. We have taken this transpose means both are of same order. Forces corresponding displacement are of same order. When you want to multiply by the two matrices of same order, one should be transposed of the other. Because column of one should be equal to row of the other, then only multiplication is possible. That's why you have to write this always transpose. Though I say in principle it is just a product of force and displacement in matrix notation, so one should be transposed of the other. And they should be of same order, then only this multiplication is possible. So similarly, this external work done will be stored within the element, right, by development of internal forces and internal displacement. So that we call it as the strain energy, internal strain energy. Due to external force, internal strain will be developed, and due to that internal strain, internal displacement will occur, right? Internal deformation and internal displacement. Because of that, you will have internal force developed, and that because of that internal work done, and that internal work done is called internal strain energy because of strain on account of external load. Internal strain energy is given by, again it is a work done by product of internal work force and corresponding internal displacement. Same as this is the internal work done, that's the external work done. Internal work done is internal forces developed, or internal stress, and internal strain corresponding to that, if you take stress or strain. So when you have these, therefore, but for equilibrium, you can say external work done is equal to internal strain energy stored. Internal strain energy stored. So that is PS dxt is equal to PM dmt. Here also why it is dmt means same argument as I use for this. They are of same order, and then you have to multiply. The work done by force and displacement, one should be transposed of the other, either PMT, DA, or vice versa. So this we have. Now, you have this relationship. Because I am trying to derive this. Right? I have this relationship. dm equals RDF. So you transpose this and substitute in this. So transposing 1, we get dmt equals RT dx. Correct? This is what you are going to do. RT dst. RT dst. So, this I will substitute in this. Therefore, we get ES DST is equal to EM. Instead of DMT, I write this RT DST. This is the answer. I will get ES is equal to RT EM. This is what the principle of Contra. It is very simple one. This principle of Contra we can obtain by this reaction but then to income strain energy. And using this principle, we can find the relationship between global and local stiffness matrix. So this is another information you should have. It is only purely fundamentals, basic concepts, as well as the matrix form of force displacement relationship. Using both, we have derived. Already we are using in our problem. Now we will continue with the problems. We continue with B problem and plane problem. Now we will go for working the problems on B. So you take the example of B and apply this principles, whatever you have, hitherto whatever it has been discussed and told. So we use those principles for solving the internal forces.